So what is auxiliary code then? Again, just to remind you, it's also known as helper code. So it has three main purposes. One, to make it easier to write properties. So that's why it's called helper code. It helps the properties. Two, it makes the problem easier for the tool to evaluate, especially in formal. It often makes it a lot simpler to debug and understand as well. And the third reason is, and this is the reason we're using it in this case, is that it can do things which assertion languages cannot do. Okay, so we can't describe that property just using SVA. Where does this code go? Well, we've already had the answer for that in a previous section on reuse. It goes inside of one of these verification components. So what do we do instead then? So remember our requirement. This is our requirement, and what we can do is create an abstraction model. So this is an abstraction not of our design. This is an abstraction of the verification problem we've got. Okay, which was to check that we have a grant within a window, and this has to work for overlapping grant. So what we say to ourselves is, okay, well, 2 represents the minimum delay for the grant response, 8 represents the maximum delay, and we can also parameterize that, of course, and we can extend the same idea to using data values instead of just request. So what do we do then? We feed in from the right hand side the request into a shift register. So this shift register has 8 elements because that represents the maximum delay, and we notionally partition that shift register into 2 parts. So as we're shifting the rec in on different cycles, it obviously will propagate from right to left. It will propagate down here until it comes out at the end there. So when it's in the end location, that's the signal called max rec. So if the request is in this part of the shift register, it's too early to be seeing a grant yet. If it's in this part of the register, it's the correct time to be seeing a grant. Okay. So what do we do then? We write some auxiliary code, and what this is auxiliary code. So notice it looks like just Verilog RTL code, system Verilog RTL code, and it has to be because the formal tool won't process it otherwise. Okay, so if you're using formal, it has to be synthesizable. And all we're doing on this loop is we're iterating around the end index 7 up until this index here, and decrementing on each iteration. So we're starting at the left hand side, because what we wish to do, if there is a grant, we want to clear the oldest request, and the oldest request will be the furthest to the left because it's clocking from right to left, clocking down here. So we start at location 7, which is this one, and we work backwards until we find a 1. Okay, so if we've got a grant and that bit of the shift register we're currently looking at, governed by the loop variable I, is a 1, then we set that bit to a 0, we clear it. Okay, and then we exit the loop because we only want to remove 1 request at a time. And what this allows us to do, once we have this code and this abstract model here, it's very simple, of course. You know, we just have to describe a shift register and this simple for loop. And then notice our properties become really easy now. It's in fact the same cycle implication, okay? Which is exactly the same thing as a Boolean in this case, because both operands left and right are Booleans. So what we're saying is if the 1 reaches this end location here, what we're saying is there must be a grant. Okay, because that's the maximum window. That's if the grants survive that long to get to the end there, that's the last cycle at which we can see a grant. So if the 1 reaches there, the request reaches there, then we must be observing a grant. Moreover, if we have a grant, it must mean the number of 1s in this part of the shift register here must not equal to 0, because if we did, that would mean we're getting a grant for no reason. So it sounds too good to believe, but it's true that a simple model like this, simple auxiliary code and simple assertions solve our problem that we couldn't do any other way, and it's really easy to understand, really easy for the tool to evaluate, especially formal tools. So go back over that if you're unsure, because this is really a crucial point. Much of auxiliary code looks like this in formal. You've got simple abstract models of the verification problem, and you've got simple properties, and it's a combination of those two that mean it's easy for the tool and easy to understand.